Hello and welcome to another creative coding video. Today we're going to go in a new direction and look at mathematical functions and how they can help us create interesting designs. Now you might be thinking, oh no, mathematical functions. Now I can't blame you entirely if you feel that way. It's true that many of us had horrible lessons at school going through mathematics, and it certainly wasn't interesting or exciting, and too often it wasn't clear what mathematical functions had anything to do with art and visual design. So I'm hoping to change that today. Don't worry, there's no need to be good at maths, there's no need to know a lot of algebra. We're not going to do any algebra or writing pages of equations. We're not going to do that at all. All we're going to do is take advantage of the shape and patterns in some of these mathematical functions and use them to help us make designs. Now that sounds a bit abstract, but that's okay. It'll all make sense when we actually do it. So let's start right at the beginning with the most simplest thing of all, which is numbers. Now let me write down a series of numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's easy enough, wasn't it? Now I could call that column or those numbers and give it a name. Let's just call it X for now. Now let's use those numbers to calculate another number, and let's say this new one is called Y. And what is that number? Well, let's say it's X plus 2, just to keep it super simple. What does that mean? What it means is that whenever X is 0, Y is X plus 2. We've said that. X is 0, so Y is 0 plus 2, which means it's 2. And let's try it for another one. Let's say this one, 5. When X is 5, Y is X plus 2, Y is 5 plus 2, which means it's 7. Now you can see already that Y is 2 greater than X. That makes sense because we've defined it that way. We've said Y is X plus 2, so you can expect the numbers in this column to be 2 greater than this one. That shouldn't be a surprise. Let's work through a few more. Let's look at the last one. When X is 10, Y is X plus 2, 10 plus 2, so it's 12. That was easy enough, wasn't it? And I could do the work to fill all the others in. Because it's an easy calculation, I know what the answer is going to be. Got that one wrong. Hey. Now you might think, oh, I did that a bit too quickly, maybe I'm wrong. Let's pick another one. Let's say 9. X is 9, Y is X plus 2, which is 9 plus 2, which is 11. If you're not believing me, have a go yourselves. You can use a pen and paper or a calculator, but this is kept deliberately simple, so we're not too kind of distracted by that calculation. Now we've got 2 columns of numbers, and the one on the right, this column of numbers, is related to this column of numbers by this relation that we've defined. It's not a particularly complicated relation, it's just the numbers here are 2 greater than the numbers here. Easy peasy. Now, what did we mean by shape of mathematical function? Well, this definition of what Y is in terms of X, that's a function. It's a little bit like our code functions. In fact, the origin of the word is the same. It takes something like X and pops out something else, Y. So you can see there's a relationship there with code functions. Right, let's see if we can bring a shape out of this. Well, if we plot a chart with all these x's and y's, maybe we can see a pattern. Let's try it. Most spreadsheets will have some kind of charting, graph plotting function. Let's see what this one's got. Okay, that's a bar chart. That's not quite what I wanted. I wanted a line chart. And I'm going to make sure that all the little dots are visible. Right, make that a bit bigger. So what have we done here? What's been plotted? Well, let's pick a number 4. When x is 4, y is 6. And on the chart you can see when x is 4, y is 6. And we've got a circle, a little dot there. Let's try another one. When x is 8, y is 10. X is 8 here, all the way up to y is 10. And as these are growing, you can see this line is rising. That kind of makes sense. And it's a straight line. Doesn't really surprise us. These are going up in regular intervals. You know, each one is one bigger than the last one. So that makes sense that there's a straight line there. Okay, so that is a straight line, and that is a shape of this function here. Y equals x plus 2. That's the function, and this is what it looks like in visual form. So that wasn't too difficult, you know, all we did was very simple adding and drawing a picture of those pairs of numbers. Easy peasy. That's perhaps not an interesting shape. Let's try a different function. Let's say that y is not x plus 2, but is y equals x times x. And some people might know that as x squared. Let's just leave it as x times x. Y is x squared. So when x is 0, y is 0 times 0, which is 0. When x is 1, y is 1 times 1, which is 1. When x is 2, y is 2 times 2, 4, 9, 16, 25, 36, 7 times 7 is 41, 30, no it's not, 64, remember my times tables, 64, 81 and 100. Now let's just pick some of these to make sure that they are correct. I think one of them might be wrong. 7 times 7 is not 41, is it? 7, my brain's gone blank. 49. There you go. Right. What's happening here now? Well, that picture now shows a line, but it's curved. Why is that? Well, if we look at these numbers that we've calculated, y, based on x, the x is going up, you know, in a very uniform way. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are also going up, but unlike before, they're not going up in a regular way. They're not going up in a regular step. The jump from 0 to 1 is 1. The jump from 1 to 4 is 3. The jump from 4 to 9 is bigger. It's 5. The jump from 9 to 16 is bigger. What's this? It's 7, isn't it? Yeah. And so on. And the jump just keeps getting bigger and bigger. These numbers are getting bigger faster, and you can see that on this picture that we've drawn. This graph of this function shows us the shape of that function, and it shows us that the y values get bigger and bigger, quicker and quicker. Now, a little bit of terminology just in case you come across it elsewhere. When we were drawing straight line graphs, those are called linear functions, and it makes sense now, the lines are straight. This is not a linear function. In fact, it's got a fancy name, a quadratic function. But for our purposes, we don't need to know that. We just need to know the shape of this function. That is interesting, isn't it? Let's stop now with the spreadsheets, because we've seen how we can draw the shape of a mathematical function. So just to quickly recap, a function takes something like x and spits out something like y. So it takes an in and an out. The numbers that we put in were just the regular normal numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the function decides what the number coming out is going to be. And depending on the function we use, these numbers can change in a very simple way or in a much more interesting way. With a simple way, we saw that they grow in a very linear, steady way, and we saw that in the graph. It was a straight line. And now we've seen an example that isn't a straight line. And this function, y is x squared, y is x times x, seems to produce a shape, a curve, which seems to go up and up, quicker and quicker. That's all we need to know from this section, that we can have functions and that we can create pictures of their shape, and those shapes can be different. Let's now move on and use a tool which draws these graphs really easily without us having to do all this work. I went through that all this work just so we know where these graphs come from, because if I jumped straight to that, it would have been a bit of a mystery, and I don't like leaving mysteries like that. So we've now seen how these graphs are made, and we now don't need to do all this hard work. So I'm going to close that. Pop. Now this tool, it's a website called Desmoscom, and it's got a graph plotter, and it does all the hard work behind the scenes and shows you a graph, a picture of your function. Now let's type a really simple one, a bit like the one we did. Y is x plus 2, and you can see it's a straight line. It's done all that work, it's done all the calculating of all the points, which is nice that it can do that behind the scenes. There, so let's just check a few of those points just to make sure it's right. When x is 0, y is x plus 2, 0 plus 2, y is 2. Yep, that's there. Let's try 4. When x is 2, y is 2 plus 2. Sorry, when x is 4, y is 4 plus 2, which is 6. That's up there. And this is showing negative x as well, not starting at 0. So let's just check that works as well. When x is minus 4, y equals minus 4 plus 2, which is minus 2. So that's right, it's there. Okay, well, I've probably talked a bit too much about that. Let's draw another one. Y equals x plus 1. And this picture now is showing both of those functions. And you can see that one is a little bit lower than the other one. And that makes sense, because this one is x plus 1 and this one is x plus 2. So it's higher up because the numbers are a bit bigger. What's the other one that we drew? We did y is 3x. Let's get rid of that first one. And we compared it to y is 5x. And you can see one is steeper, y is 5x is steeper than y is 3x. And if I do another one, y is 0.5, like half x, and you can see that's not steep at all. So this number 5 seems to make the line much steeper, and that makes sense because it's multiplying it by a bigger number. When x is 2, 5x is 10. When x is 2, 3x is 6. Up there. When x is 2, y is half x, it's 1. That makes sense. If you're not convinced, have a play with a bit of paper and a pen, or use this website. Okay, so these are straight lines, not that interesting. Let's try that other one we saw. Y is x times x, or x squared. Now, isn't that interesting? It's what we saw, but we only saw a portion of it before. And you can see it really does zoom all the way up. Magic. I wonder if we can do what we did before and make it even steeper. 5x, we can use that squared there. X squared is the same as x times x. And you can see the blue one, the blue curve, shoots up even faster because it's 5 times taller than the other one. And we can make a shallower one. We can say y is 0.5 times x squared. That's a bit shallower. Let's make that even smaller. We can edit these. We can say 0.1. That's much more shallower. 0.01. Quite shallow. There. Now this, you really should go and have a play with this yourselves, because it's a really easy way of getting a feel for how these mathematical functions behave in terms of their shape. And we use that spreadsheet and we work through the numbers, but we only do that so you know how these lines, these curves are created. Now you might say, okay, that's mildly interesting. I'm going to show you another function which is much more interesting. Now, before I show it to you, I want to say you don't need to know where it's come from, or have seen it before in lessons, or know a lot about it. All we're interested in is the shape. So let's type it in. Y equals, and I'm going to type sine of x. There. Now, isn't that interesting? It's going up and down in a really rather nice, smooth, curvy way. And we can take advantage of that when we code. We'll come to that. But isn't it amazing that there are mathematical functions which don't just behave as straight lines or curves? This one seems to go up and down, up and down, up and down. I didn't really expect that from a mathematical function, but the reality is that there are mathematical functions that have all sorts of interesting shapes, and sadly we don't get to see them in school. Certainly not as much as we would like. If you are interested, this is called a sine function, and that's a sine wave. And if you're into electronics, or if you're into sound and music, you might have come across them before. Okay, let's have a little play with this, just so we can get a feel. So let's try that trick. Well, it's not really a trick. Let's try that method of making it taller. Let's say 5 times sine x. And you can see that reddy orange one is taller. In fact, it's 5 times taller. Let's see if we can make a shallower one. 0.5, which is a half times sine x. Let's get rid of that tall one. There. You can see the blue one is not as tall as the original one because we've halved its values. That is interesting, isn't it? There is something else we can try, and that is not multiplying here like 5 times x. Instead of doing that, let's multiply x before we give it a sign. And you can see, look, it's going up and down much faster. And the reason for that is that x multiplied by 5 increases much more quickly. So it's as if it's zooming along the axis much more quickly. And in fact, if we did it 3, it doesn't go so fast. 2, and we can even slow it right down. There. And we can make it really high, like 20. That's interesting. Okay, so enough theory for now. We've seen a really interesting function. Let's go and do some coding. So the first thing we should try and do is to see if we can use mathematical functions in our code. So what I'm going to do is I'm going to use code to count up some numbers and then work out a mathematical function from them. So we're going to count up x and work out y and then draw them. So let's see, let's use a loop. If you need a reminder of repeat loops, go and have a look at the previous videos. We've done lots of examples now using repeat. So we say repeat. I'm going to use a loop counter which starts at 0, goes up to 800. You can see this is the canvas size. So x is going to go from 0 to 800 in steps of say 10, and I'm going to pass that counter to my maths function. That's a function I'm going to define. So I need to do that now. I'm going to say function my maths function, and I'm going to have it receive. It needs to receive that loop counter, otherwise it won't work, and we'll call it x, which is convenient because we're going to be using it as the x coordinate. So we've got x, which is going to be 0, 10, 20, 30, 40, all the way up to 800, and we're going to work out a y from that. Let's say it was, let's start with a simple one, x plus 2. That was the very first one looked at. Let's just pause there and let's connect what we've just typed here with what we did right at the start. We had numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and those were x, and we calculated y from them, and we said y is x plus 2. So here the first value of x will be 0, passed all the way through to the function 0, and it will calculate y, which is 0 plus 2, and y will be 2, and it will do this for every x that this function gets from that repeat loop counter. Now let's do something with those x and y's, and let's maybe plot a circle. X comma y, make it size 5. Let's just see what that does. I'm not too worried about styling at the moment and getting the right colours. I don't think I've made any typos. Let's see. Okay, that is a straight line. It's going down, and you'll remember why that is. To remember the canvas that we've got, 0 is in the top left, not the bottom left. So normally in school we had, and most graphs that we draw, we have x and y, and the origin 0 is in the bottom left. So 0, 1, 2, 3, 4, 1, 2, 3, and we might have had a line that goes like that. Well, this time, because of the way this programming language works, we're starting 0 here. So x still goes along, and you can see here 0, 100, 200 up to 800 that way, and y goes down that way. So x, y. And then as x and y increase, we get a straight line going like that. That's why it appears to be going in a different direction to the line that we had here. Let's remind ourselves, y is x plus 2. That's going in that direction, but ours is going in this direction. Okay, that's not that interesting, is it? Let's try that x squared one. X times x. In fact, squared, there's a little instruction called SQ or squared which does that for us. Let's plot that. What's happened there? Well, it looks like there's only 3 dots on the canvas, and that's because it's zoomed off the canvas really quickly. Why is that? Let's look again. X squared, 0 squared is 0. 100 squared is 10,000, which is all the way down there somewhere. So this really zooms off the canvas very quickly. So we need to slow it down somehow, because those numbers get big. So 800 squared is some huge number. We've already seen how to slow down these functions. We can divide it by, let's divide it by 100. So when x is 800, it's going to be 800 divided by 100 is 8. Let's see what that looks like. That's kind of a slow one, isn't it? Let's fiddle with that. Let's make that 10 divided by 10. There, that's quite nice. That's that quadratic curve again. Okay, let's try that sine function. Sine x. Wasn't that supposed to be a wave? Up and down, up and down. What's happened? The reason I've deliberately made this error is to show you some of the characteristics of that sine wave, which we need to keep in mind when we use it. So let's look again at that sine wave. Y equals sine x. Now, what's the maximum value of this sine? It goes all the way up to 1, and the minimum is -1. So it goes up to 1, down to -1, up to 1, down to -1. On a canvas, up to 1 is tiny, and down to 1 is tiny. I mean, I can't really draw something as small as 1 up and 1 down. It's tiny. So when from here to here is 100, going from 0 to 1, -1, it's going to be almost too small to see. And we can almost see it, but not really clearly. So we can stretch it out, we can make it taller, we can say 100 times sine x. That takes the sine wave and makes it taller by 100. There you go, up and down, but it's chopped off the end of the edge of the canvas. Let's shift it down. We can say 300 plus whatever we had before. That has the effect of shifting it down the canvas by 300. There, much better, isn't it? That is much nicer. Now that on its own could be an interesting design. It's certainly a nice curve. We could try some styling things on it. We can say no stroke, so that it doesn't have an outline, and we can change its colour to, I don't know, let's just say something a bit darker, red maybe. What we could do is make it so that, well, I was going to make those circles larger, but instead of doing that I'm going to change my repeat loop so that it goes up not in steps of 10 but in steps of 5. So smaller steps, so more circles should be drawn. Yep. I like the way that it bunches up on the peaks. It's quite nice. And what we can do, maybe, is draw 2 circles. So for every xy, we draw a circle at xy, but maybe we do another one that's shifted up and down a bit. Maybe we'll do that a little bit bigger. Just an experiment, just having a play to see what kinds of things we can do. That's an interesting design. Now you might be thinking, okay, yeah, that's certainly a way of drawing interesting patterns on the screen. But there is more we can do. What if I didn't use that sine wave to position the circles, but used it to do something else? What am I thinking about? What's on my mind? Let's see. Let's delete that. Let's draw the circles at x. Let's draw them at y down so that we get almost, well, that's a line, isn't it? Let's make them go up in steps of 10 again and make the circles a little bit bigger so we get a line of circles. So this is nothing amazing here. This is just a very simple repeat instruction with a loop counter that goes from 0 to 800 in steps of 10, and we're just drawing a circle at x, which is a loop counter. We've done that lots of times. But what if we said, instead of drawing it, instead of changing y, why don't we change the size? So we say, create a new variable, size s, say, well, we might as well call it size. Size equals something to do with the sine. And because we know that goes just up and down, +1 -1, let's make it bigger, 50 times. That's a bit big, maybe 20 times, and let's call that size. So let's just repeat what we've done. We've got a loop counter that goes from 0 to 800 in steps of 10, and that's passed to a function called myMaths function. We're going to draw a circle at x, 300, which goes along the canvas just like we saw, but the size of the circle depends on sine x. What do you think that'll do? The size depends on sine x, and sine goes up and down in waves, so the size of the circle should go up and down in waves. Let's see. I have a feeling this will be interesting. Isn't that interesting? That is nice, isn't it? Let's put that stroke back in. Let's comment that out. Yeah, that's interesting. Let's make them a bit bigger and space them out a bit. That didn't work quite so well. Just messing around with some of the sizes. Let's make it massive. Let's make them grow big. 50. An interesting effect. Now, okay, maybe this isn't the most, award-winning design, but the important point is we've now created a design which makes use of something that's changing in a sinuous, wavy way. before it was the position up and down, and now it's the size of the shape. And it's all come from a super simple line of code which uses sine of x. This is the magic line that determines the size of the circle. This line, you know, we've seen lots and lots of times before, drawing a circle at a location of a certain size. We've done that so many times we might be a little bored of it. But this magic line takes x, the position along the canvas, and applies the sine function to it, which we know is wavy, has a nice beautiful shape. And we've just stretched it a bit so it's bigger. Isn't that interesting? I like that, that's nice. In fact, one thing you can do, which is one of my favourite techniques, is we can say no fill, so there's no fill colour, but there is a stroke, the outline stroke. Let's see what that does. There, that's nice, isn't it? And in fact, if I say a darker colour, that's a bit more prominent. There. It's rather nice. And I can slow it down by halving x, like that. And I can speed it up by making x larger by multiplying it, maybe by 3. There. Well, that's probably a bit too much. Let's try it there. It's interesting. Let's look at something else we can do. This is one of my more favourite things to do. So we'll go back to having a circle of a size, let's say 10. Let's make them bigger. There you go, a bunch of nice circles. I'm going to turn them back to, in fact I'm going to say no stroke for now. No stroke. So they're just filled normally. And now what I'm going to do is use a sine function, not to position it vertically, we've done that, not to change its shape, size, which we've done that, but to choose its colour. So I'm going to say var, remember the RGB colours? I'm going to say red is, say 0, var G is, I don't know, let's say sine of x. And actually that goes up to 1, doesn't it? -1 to 1. So let's multiply it by 255, because we know the red, green, blue values have to go from 0 to 255. And for blue is, let's just say 128. So the mixing of the colour is going to mix 0 red, 128 blue, which is half the blue, and it's going to mix a green element, which is going to be a bit wavy. Let's just see the effect. I don't know what this is going to do. It'd be interesting to see. Oh, I didn't use those to actually pick a colour. I calculated them and didn't use them. There. So I'm using a fill instruction to pick a colour for filling the circles, and I'm saying red, green, blue, which we've just set here. Let's see. Yeah. So you can see the colour is changing, but it's changing in a sort of smoothly waving way. Let's change the sizes of some of those so you can see that more clearly. So I'm drawing more smaller circles. There. You can see that now, can't you? The colour is changing smoothly and it's undulating, it's becoming a deep blue and then a deep green and then a deep blue, and it's not a sort of a sharp transition, it's a smooth transition from one to the other and back again, because that sine wave changes up and down smoothly. In fact, if we drew rectangles, let's see, 0 x, and its size, let's say 10 going down to 600. So what we're going to do here is draw a rectangle which is a thin strip from the top of the canvas to the bottom, and there's going to be lots of them across the canvas. Shall we illustrate that on our sketch? So what we're saying is we've got a rectangle instruction, and it's going from x, 0, 10, 600. Let's see if we can work out what that does. Well, whatever x is along, let's say it's 100, the rectangle is going to start there, and it's x along and 0 down, so that will be the corner. It's going to have a width of 10, which is this number here. It's going to have a height of 600, so it'll be something like, if we can draw that right, there, a long thin rectangle. Let's fill it in. And when x is a bit bigger, let's say 200, it'll be a thin rectangle that goes all the way down there. And if we're using a loop counter for x, you can imagine now that we're going to be drawing rectangles all the way down the entire canvas. That's what that instruction does, even though it looks just a simple single line. There's quite a lot of thought in that, but we're filling it again using a combination of red, green, blue, where green is a little bit wavy. Let's see the effect. There. Isn't that interesting? So we're cycling through some colours, and the transition is smoothish and wavy. The reason it's not super smooth is because we're jumping in steps of 10. We could jump in smaller steps. We can jump in steps of 5 and make the rectangle thinner. There, much smoother, isn't it? And we can play with let's make that 128 times, though it's not quite as tall as the other one. Just experiment to see what happens. Not a massive change there. Maybe if I said that was going twice as fast. Oh, that's interesting, isn't it? We're combining two waves of a different sort of frequency. Some are slower and some are faster. Let's try that with the full height, 255. See if that makes any... Yeah, there's a big difference there, isn't there? So you can see now that it's possible to use that mathematical function, the sine wave, and take advantage of it to, number one, position shapes, number two, give them size, and number three, pick a colour. So we've illustrated in 3 ways using the sine function. Now there are textbooks and mathematics books full of sine, and they're used for all sorts of things, but for our purposes we're just interested in its up and down shape. Now let's go back to this graphing calculator and look at some other ones. We're not going to explore them all with code, but I'm just going to show you the shape so that you can hopefully look at it and say, aha, I could use that. Let's look at a related one called the cosine. It's similar, you can see In fact, it's the same shape, just shifted along a little bit. So sine starts at 0, but the cosine, the cos, starts at 1, and that can be useful. Sometimes you want to start high and sometimes you want to start at 0. Another interesting thing that's worth playing with is multiplying the sine by itself, so squaring it. So let me put some brackets around that, like that. So we've got a sine, but I'm squaring it. Now what can you see? Well, when you square a number, negatives turn into positives. So you can see this green curve, which is sine x all squared. It does go up and down, but it never becomes negative. It goes from 0 up to 1 and then back down to 0, but it never becomes negative because squared numbers are never negative. So when this is -1, this one's actually 1, because -1 times -1 is +1. So that can be useful as well when you don't want it to go below 0. Is that useful for us? It is actually. Let's see it again. With that simple example we had, you might have noticed there's a bit of a gap here. It's going up green and down green, but then there seems to be a bit of a gap. That's because the green element here became negative, and we can't really mix negative green. So what we could do is square it. We can say sine x squared. That means it'll never be below 0. There, and now we've got a much smoother and more regular transition from red to green. It's nice, isn't it? I like that. What if we did it with red? It's fun, isn't it? I can't help myself. Wow, that is nice, isn't it? That's really nice. Yep. It's simple. I'm deliberately keeping that simple. There are more interesting things you can do. Let's get back to the graph plotter. So that's one thing you can do. Something else that can be useful is when you multiply sine waves together, but they've got a different speed or frequency, as it's called. There. Can you see what's happened? So let me draw that. Y is sine 5x. So we've got sine x, which is going up and down. We've got sine 5x, which is going up and down really rather quickly. And now I'm going to multiply those together. Oops, let me type that properly. Sine x. Get rid of some of those. You can see that this one goes up and down, but stays within the envelope of the other one. Let's delete that so you can see that more clearly. So it's up. The ups and downs are big, and then the ups and downs are small. If I make that 10, you'll see that even more clearly, or even 20. That's nice, isn't it? So it's up and down, up and down, up and down, but the ups and downs themselves are modulated by the slower sine wave. And that could have creative uses. Imagine drawing shapes of that size, or position, or colours. That's interesting. That is nice. There are, of course, other functions, not just sine and cos. One of them is the exponential function, which gets bigger and bigger. You might have heard the phrase getting exponentially large. That's where it comes from. And it goes up faster than even the x squared that we saw. Now, that might not be as useful. It could be useful. If I put a negative, it's going the other way. It's decaying to 0. Now that could be useful, having something like colours or sizes fall off as a decay. So let's zoom into that a bit there. There. Oops, I need to mess that up a bit there. There, so you can see when x is 0, it's 1, and it decays towards 0, but never quite gets there. So that could be useful. More often, a different version of that is used, which is this one. So we've got x squared inside that bracket minus, and then the exponential of that. And you can see there's a difference there already. You can see that it starts to fall slowly, then quickly, then slowly. So it's almost like it's rolling off, then falls quickly, but then slows down. Let's hide the other one so you can see. And then that one. So you can see why this one is used. It is actually used a lot, this kind of bell curve as it's called. You might have heard that phrase as well. Again, it's a mathematical function and it uses some mathematical blah blah blah, but it's the shape that's important for us. And when we want something that's rolling off smoothly, that could be useful for us. Let's try and use that actually in our code. Let's try and pick the red component to be, so we had an exponential function which I think is math.exp, and we had minus x squared, so it's minus squared of x, and I think we might need to scale that, so let's divide that by 100. Let's see what that does. I've not done this before, it might not work. Not quite. Oh, I know what I did wrong. I forgot to multiply that by 255. Because this thing is going to go from 1 down to almost 0. But our red, green, blue values need to go up to 255, so I need to scale that up a bit. Let's try that again. Yeah, that's it. Let me stretch that out a little less. If we stretch that out a bit more, you can see it falls off more slowly. It's very smooth, that transition, isn't it? Let's look at that again. There, a beautifully smooth transition. But it's not linear, it's not a straight line, as it were. It starts off changing slowly, then quickly, then slowly again, which is what we've got here. That's really nice use for it. What else could we do with that? Yeah, okay, that's nice. So that's another function. Let's look at another one called the hyperbolic tangent. Now I like this one because it goes, if we show it, it goes from 0 up to 1 but never quite gets there, and that can be useful as well. And on the other side it goes from 0 to almost -1, never quite gets there. That's used quite a lot as well. So this has been quite a longer video. I'm going to finish off with an example of an interesting design that makes use of these mathematical functions. I'm going to just remove all the code so I can talk through what I'm going to do. So what I'm going to do is have a function called particle, and I'm going to call that particle function lots of times. Let's say I'm going to call it, I don't know, 500 times, and I'm going to, there it is, my particle. So I'm not using the loop count, I'm just using a very simple repeat. I'm just calling particle 500 times, and what this function is going to do is going to pick some X and Y locations. I'll fill that in a second, which are random on the canvas. So random number between 0 and 800, and a random number between 0 and 600. So that means X and Y will be somewhere on the canvas. And we could draw a circle at X, Y. Could do that. And give it a size of 105. We'll just do that for now, just to get started, just to check that code works so far. 500 random circles, they're a bit big, let's make them smaller. Okay, yep, lots of them. In fact, I'm going to vary the size. And do you remember before we said var size is something to do with the sine of X, maybe? Well, we could do that, but I'm not going to. But I'll just show it again, just for practice's sake. So those random circles will have a size that varies as they move along the canvas. Easier to see, so you can see that's quite large, isn't it? Let's do that. Let's make this a bit bigger, just to make it clearer. So you can see almost that there's bands, vertical bands. If I draw more of them, actually that's quite a nice design on its own, isn't it? Let's see. Yeah, that looks nice. Is it soda pop or something? Bubbles. Let's draw 1,000 of these. There, now you can see as we move across the canvas, the sizes start off small and then grow and then go small again and then grow and small again, then grow, then small again, and it's a smooth wavy transition. That's because the size depends on a sine wave which is fed the X coordinate. That's we're starting to see an interesting way of shaping those circles. Now, what would happen if we said the size doesn't depend on X, but depends on the distance from the center of the canvas? So let's go back to those circles again. Got lots of circles. Now in the middle of the canvas is somewhere here. Now each of these is a different distance from the center. So this one is quite close to the center and this one is quite far. Let's make a sign that depends on the distance to say D for distance, and we need to define that D, and it's the distance of this circle which is at XY from the center which is at 400, 300, and there's a nice function that's already there called dist, which works out the distance between this point and this point. So this is the center of the canvas and this is XY. Let's draw a picture of what we're doing there. So 400, 300 is the center. We might have an XY which is here, XY, that's 400, 300. So the distance is that distance there, and that's what dist X, Y, 400, 300. That's what that works out. Now XY of course could be anywhere. It might be close by here, so it'll be that distance, or it could be quite far and it'll be that distance. But wherever XY is, this thing here works out that distance, and that's useful for us. So that's the distance of the little circle from the center of the canvas. Let's see what effect that has now. So we're pushing that distance into the sine function so it will go up and down, and then that'll be used as the size. Let's see. Interesting. So we're starting to see almost like rings. We've got an empty centre almost with tiny circles, and then they grow larger, and then they're smaller, and then they're larger, and then they're smaller again. So this is using the wave and making it depend on the distance from the centre. That's why we've got rings. If we draw many more of these things, of these little circles, that should be even more evident there. If we used a square of that, then that might make a different effect. Yeah. Did I prefer it the other way? No, this is nice. Yeah, that's nice. And we can, of course, use colour. We can say for red is 0, for G is 0, for blue is 255 times sine distance. Or we could just say it's actually, let's say the distance divided by, I don't know, 4. Let's just say, see what effect that has. So we're saying we're creating a red, green, blue mix, fill, red, green, blue, and the red and green are 0, and the blue depends on the distance. That's a bit dark, isn't it? Let's make that 128. Interesting. Yeah. Let's make that green depend on that sine function. So mixing a bit of green in, but that one depends on the sine of the distance. Interesting. Isn't that interesting? And you can have a lot of fun now with using that sine function to pick colours, to pick the sizes of these circles, and you can spend hours experimenting. But this interesting design, this interesting pattern, remember it is fairly sophisticated, I guess, but it's designed based largely on that mathematical function, the sine wave. And that's really what I wanted to show you, that those mathematical functions, they might have been boring at school, but their shapes are interesting for us. We can take advantage of the ones that decay, or the ones that shoot straight up and explode in an exponential way, or the ones that go up and down in waves. And we can use those shapes for colour, for location, for size. I'm tempted again to experiment here. That's nice. You could just go on experimenting, couldn't you? It's kind of endless. Yeah, have a go yourselves. I mean, look at the code. It's not particularly long, is it? We're just repeating a function 2,000 times, and we're picking a random location for a circle, working out how far it is from the center. We're picking a color, red, green, blue, and we're making it depend on that sine wavy function. And we're also picking a circle size that depends on that sine wavy function. You notice I've been a little bit informal with the, calling it sine wavy and sort of sinuous and, up and downy, and that's fine. We don't need to be overly kind of obsessive about correct mathematical terminology. No one's going to tell us off. We can just use these to have a bit of fun. So have a go yourselves. I'm really tempted to go on and on, but I will stop. It's already quite a long video. What I'll do next time is do a shorter video with a different worked example using a mathematical function. But for now, I hope that you've seen the main points, which are mathematical functions are easy to understand. They're just numbers turning into other numbers, and some of them have boring shapes like lines. Some of them have more interesting shapes, and the very interesting shapes we can take advantage of and use their shapes for colour, location, size, and other things too, I'm sure. Okay, well, have fun, and we'll see you next time. Bye.